Hello. Today's video is going to be about controlling a mass on a spring, a mass damper system. And before you get around to saying, well, oh no, yet another second order video, I'm going to tell you that this is going to be different, and I'll explain why. First, most of the videos are trying to explain how you can calculate the natural frequency and damping factor from looking at the waveform. And I've seen those videos, and my thoughts are that's not the way you do it, except for maybe to get a rough estimate. If you want to do it correctly, you use a system identification, as I have shown in some of my other videos. The other thing I want to get across is that if you're looking at a system that's already been designed, well, that's one thing. What I want to do is explain how you design the system to get what you want. So I'm going to first start with the definitions, and these are the standard definitions right here. There isn't any difference between what I'm doing here and anybody else, but I'm going to get into controlling this. So let's just scroll down a bit. I have my second order system here. Right now it's pretty much undefined as to whether or not this is overdamped or underdamped. If A1 is less than 2 times the square root of A0, then it's going to be underdamped, and that's going to be the case in this example. I have a PID controller, and the reason why I have a PID controller is because this system has 2 poles, and so you need 2 gains to place the poles. The integrator comes with its own pole, so basically you end up with a closed loop system with 3 poles, so I need 3 gains. The closed loops formula is this. So I got the controller and the system. This is the mass of the spring. I'm calling that the system. And this is the general formula. And if I do the substitutions and simplify, I get this as my closed loop transfer function. Now, notice that there's a gain for each power of S, and that's necessary to place all the 3 poles. And normally this system is going to be very, very underdamped. In fact, you'll see later I chose parameters that make it almost as bad to control as a slinky. But what I want to do is I want to place 3 poles at minus lambda. So this is my desired characteristic equation. This is the actual characteristic equation. And what I need to do is find a way to adjust these gains so I get something that looks like this. So to do that, it's fairly simple. I've shown this in other videos. What you have to do is you match each of the coefficients of S. In other words, I got lambda cubed here is going to be equal to A0 times Ki here. And I can solve for Ki, and this is the symbolic formula for the integrator gain. And then I can do the same thing for the proportional term. I got 3 times lambda squared is equal to this. So when I solve, this is my symbolic formula for the proportional gain. And then I can do the same thing for my derivative gain. And it's necessary to have a derivative gain because if this term is very low, then what will happen is you'll end up with an underdamped system. Or more technically, you'll have complex poles. So now I'm going to choose some simple parameters to just so I have something to work with. And I've got a mass of 1 kilogram, a damping factor of 0.1 newtons per meter squared, per meter per second. This is the force proportional to the velocity. And then this is my spring constant, which is in newtons per meter. And you can see that that's pretty soft for the spring. And what I want to do is simulate a spring slinky. But I ran into problems in my first iteration of this. I'll show you what they happen to be. My original video, I had a force limit of 100 newtons, and that would require stretching the spring 100 meters. Well, that's not realistic. So what I had to do is reduce my force limit, because that's going to be based on how the spring constant and how far I can deflect the spring. So I decided I was going to just have my spring be deflected 1/2 meter at the most. So I have this limit of 0.5. So my force limit that I have is 0.5 newtons. And you'll see where that comes into play later. Now, the A0 is the spring constant divided by the mass. And the natural frequency is the square root of A0, so I have a natural frequency of 1 radian per second. That's extremely low. That's like less than 1/6 of a hertz. And then A1 is the damping, the friction force, viscous friction divided by the mass. And this is the formula for computing the damping factor, so I have a damping factor of 0.05, and that's extremely low too. So let's just take a look at how this affects the controller gains. And if I do the substitutions for A0 and for A1, you can see that Ki is lambda cubed over K times M. So in general, you can see that in all three of these, increasing the mass means that the gains are going to increase. By increasing the gain, or the spring constant, you can see that all these gains are going to decrease. And notice also that the derivative gain is only used on A1. And basically what it tries to do is make this coefficient 3. You see, if we go back up here to our desired coefficient, up here, or you see this is 3 times lambda. What we're trying to do is get to 3 times lambda. And if we're short, then what will happen is that the 3 poles will not be on the negative real axis, and you'll have something that will oscillate. So that's why the derivative term is necessary. And you can see the more the friction, the smaller the derivative term needs to be. So they're complementary. Another thing I like to do is use Laplace transforms on a step jump just to see if the system's going to overshoot. And this is my closed loop transfer function again. And I've made these substitutions, and you can see the response as a function of the raw parameters. And if I take the inverse Laplace transform, you can see this is the response in the time domain. And what I'm looking for here is this is my step, whatever it might be, 1 millimeter, 2 millimeters, however far it happens to be. And when lambda at t approaches a high number, this is going to approach 0. So what will happen is we'll end up at our final position, which is going to be r. But until then, this is going to be 1 when we're at 0. And what we need to do is make sure that this whole term never becomes positive, because if it becomes positive, it's possible that we can overshoot. And if I choose the wrong value of lambda, you can see this is a positive term, and there's some terms in here. It is possible to see that the system is going to overshoot. Now, to avoid overshoot, what we need to do is remove the proportional and derivative gain from the forward path. So let's just take a look at this. This is the forward path gains, and these are the backward path gains. So what happens is or the feedback path. And because these gains, like Ki is in both the numerator and denominator, it's working on the error between the target and actual position. But in this example, we have only the Ki gain, or the integrator gain, working on the error between the target and actual position. These other gains are only working on the change in the actual position. And this is done commonly in temperature control systems. On PLCs, you'll often see PIDs that are actually PI minus Ds, because the derivative gain only works on the process variable, or in my case, it's going to be the actual position. And you can see when I do the inverse Laplace transform that none of these gains or terms are going to be positive, so I don't have to worry about this term here being positive and causing overshoot. The problem with removing the KP and KD gains from the forward path is it reduces bandwidth, and I'll show that later. So now we're going to use our symbolic formulas and our assigned values to calculate out what the Ki, Kp, and Kd gains happen to be. Now these are gains, not time constants. So for instance, if you happen to have an ISA type of gain like a PID on a PLC, this would be a gain, but these two would be time constants. But in my case, these are all gains. So they're newtons per meter seconds. In other words, when I say meter seconds, I mean meters of error times seconds. This is newtons per meter of error, and then this is newtons per rate or velocity error. Now to do my simulation, I have to take my continuous state space arrays and convert them to the digital format. And I'm not going to get into too much detail on that. On MATLAB, they have functions that will do that for you, but MathCAD does not, but MathCAD is prettier. So now we're going to do the simulation. And what I'm going to do is a series of step changes in position, and I'm going to simulate for 2 seconds. So I have my initial values. My initial state is position and velocity. I'm going to run for n iterations, which happens to be 2,000 because my time period is 1 millisecond. I have a few steps to different positions. You can see it's only 1 millimeter. And first what I have to do is I have to calculate my output. This is my force output as a function of my Kp and Kd, my proportional derivative gains. And this is, remember, a vector that's position and velocity. This is actual position and velocity. So when I multiply that out, I get a force due to my proportional and derivative gains. I have the same thing here, only have to add it to my integrator, my previous integrator, to get the current integrator. And then I have to limit the control output, and I'm doing that by taking this L. Remember, I had to limit the output to 0.5 newtons because I didn't want to stretch the spring any more than ½ a meter. So again, this is dependent upon the spring constant. If I have a higher spring constant, this L could be higher. And then this U minus PD just keeps the integrator from winding up. I can get to that later in a different video. I sum the gains together and I get my target position and velocity, actual target and velocity, my control output, and the integrator term. Oops, this said limit force to 100 newtons. That was from my old video. Again, I'm only limiting it to 0.5 newtons now. And you can see the effect. So this is my step. I'm only going to 1 millimeter. And the reason why is because even a 1 millimeter change with the gains I have causes the output to saturate at my ½ newtons. You see, this is the scale for the force. And you can see that it gets the mass moving. This is my set point at 1 millimeter. And then after it gets so far, you can see that the force needs to go negative to break so that it gets right into position, a critically damped type response, or the same response you get with 3 real poles. There'd be no overshoot. And then the second move, I went to -1 meter, and I did this on purpose. You can see that it saturates at -1 or 0.5 newtons again, and it gets moving, but it's moving so much faster here that it needs to break. And you can see, because we have a limitation of 0.5 newtons, it doesn't break fast enough or hard enough, so it will overshoot. Now I can fix this easily by just increasing the spring constant from 1 newton per meter to 2 newtons per meter. And then here you can see it's a smaller move. Again, you can see it saturate and then do the braking. But except for this case here, which I did on purpose because I wanted to show how it saturates on both sides, will cause overshoot. You can see there is no overshoot, and this is due to the fact that I placed 3 real poles on the negative real axis. And the other thing that I did that's necessary is I kept the integrator from winding up. You can see that the integrator actually winds down and then winds back up to 0 newtons. And this little trick keeps the integrator from winding up. Otherwise, what happens is the error that builds up in the integrator between here and here, this area has to unwind by overshooting by the same area that you have here. So, let's continue on. Let's look at a sinusoidal motion profile. Now, up above, I didn't make this clear, I set the minus lambda to minus 15 hertz, I believe. Let's see what I did. Go back up. Yeah, minus 15 hertz. So I got 3 poles at minus 15 hertz. And that's pretty extreme because the natural frequency of the system is only, like I said, it's less than 1/6 of a hertz. So let's go back down to the sine wave. And here I make a small amplitude of 10 millimeters. And the reason why I can get by with that is because it's a little bit more motion than I have in the example up above, but the force necessary to go 10 millimeters is not as high as the force it takes to do a step. So I'm choosing a frequency of 0.5 hertz, and this is actually pretty extreme and usually not possible. It's usually very difficult to go at a frequency higher than the natural frequency of your system. And the reason why is because the physical system, the gain starts to drop off very, very quickly. So what happens is you need more and more force to compensate for that. But in this case, what we're doing is we're kind of generating force on paper. So yeah, we can get by with our 0.5 hertz. But if I change this to 1 hertz, you'll see that I would easily over or saturate my output, and then we wouldn't be controllable anymore. So this is my response. And you can see that it doesn't take much force. This step here is because and you can see there's a difference between the target position and the actual position, but because the velocity is a non-zero value, it's just kind of starting instantaneously at a non-zero value. It takes a little bit of force just to get it caught up. So after that, we're matching the sine wave exactly, and I'll be able to show you on the Bodhi plot to follow exactly why that happens. But this is fairly realistic. If I change my my frequency to 1 hertz, what would happen is that this amplitude would be so high, and it would take much more force to follow the sine wave. And the reason why is because the acceleration goes up with the frequency squared. So that's something to think about. So this would go up much higher. So let's look at the Bodhi plot. So I got my closed loop Bodhi plot, and this is the transfer function from above. And you can see that because I set the 3 poles at minus lambda, and that's pretty far off on the negative real axis relative to the natural frequency, you can see that I can extend the bandwidth with hardly any phase lag or change in gain all the way out to about 8 or what is that, 6 hertz or so. But again, the natural frequency is 1 radian per second, and it takes extra force to go out beyond this spot right about here. You can see that I extended the bandwidth out to 58 hertz, but that's not very realistic. Now, you can see the gain increases here. Well, that is due to the closed loop or the poles, the gains in the forward path. And just to show you that, let's just come down here and let's just remove these. So now I have no gains in the forward path, and you can see that the gain starts at 0 and it goes on down. And you can see there's a lot of phase lag here too. Let's do a Control Z and get this back. Anyway, the bandwidth is greatly reduced. So depending upon your application, you really need to look at the zeros. In this case, the zeros don't hurt us because we don't have enough power out here to cause any overshoot. And that's why in my step jumps that you saw earlier, it didn't overshoot. But if I reduce the lambda where this was down here, it's possible that we would get overshoot. So now let's look at a pole zero plot. And what I have to do is take the numerator part, and this is the denominator part. So this is where I calculate out the zeros. And you can see the zeros are here, and the poles are here. The poles are exactly where I wanted them to be. That's 15 times 2 times lambda, which is that's 94. And you can see the plot. Now, if you look at a pole zero plot, you can also tell this is going to overshoot, or potentially could overshoot, because if you start from here, from the origin, and you start scanning to the left, you get to the zeros, which add phase lead and gain before you get to the poles, which then reduce the gain and introduce phase lag. And if we had enough energy at this point, what would happen is we would get overshoot. But because the natural frequency of the system is 1/6 of a hertz, the energy kind of drops off right here, so these poles do not cause overshoot, as you've seen in the previous example. So, I wish I'd started with this first, but the big thing is, why bother? And the reason why is because the active damping, or damping a mass in a spring, is important to the automobile industry. For instance, there are companies like Bose that you normally think of for silencing headphones and such, and stereo gear. They also have active damping for cars, and that allows them to stabilize the car and avoid oscillations. Also, Audi and BMW are doing about the same thing. And it requires this kind of math to be able to do the calculations with the mass of the car and the spring constant. And one other thing I'd like to point out is when you're designing a system, this viscous friction can be a problem. Now, normally on a shock, what ends up happening is that you have an orifice where you have losses due to fluid moving through the orifice. And what these car companies are doing is they're using a magnetic oil where they can change the viscosity so that there's more force, or the damping factor goes up as the oil goes back and forth through the orifice. But there's a problem with that. I've actually visited a plant where they make shocks for tanks, army tanks. And those army tanks, you've probably seen videos of them. They're just going lickety-split across the rough terrain. They're going up and down, up and down. There's an awful lot of mass. They're going awfully fast, and the shocks are going up and down very, very quickly. That actually generates a whole lot of heat. And what ends up happening is they can actually catch fire. And I've seen a shock that caught fire. So what ends up happening is that you would like to reduce the viscous friction as much as possible and use the derivative gain, or the active damping, to provide, use the derivative gain to provide damping. And that doesn't use near as much energy, at least it isn't in the shock. Another thing that the automobile manufacturers are doing is some of them are finding ways to harness that energy that is generated so that they can pump it back into the system. The big thing is you want to avoid the mechanical viscous friction as much as possible. So I hope that you find this interesting and different from all those other, yet another second order system videos. Bye.